WCA Astroseminar. So today's speaker is Mohamad Shalaby. So a little bit of the intro. Mohamad did his university studies. Started from Ames, South Africa, and then came over here to Perimeter, where he did the TSI program.
Here is water, not Perimeter.
Yeah, jointly with water, because then continued on, stayed here. So that's where I met him. He was a graduate student working with Avery, and he did his thesis work on plasma physics, instabilities, cosmic rays, a lot of astrophysical phenomena. And after he graduated here in 2017, he got a postdoc position at the Leibniz Institute of Astrophysics in Potsdam. So I guess it's one of those ways showing that when the graduate students leave here, they go on to great success. And yeah, so Mohamad is quite the expert on plasma physics, and I think today he's going to be telling us a little bit of those things. So Mohamad, whenever you're ready, take it away.
Thanks, Boris, for the introduction. I will be talking a little bit about plasma physics. So if I say something that is maybe not very obvious or not familiar to some people, please interrupt and ask. I would like to convey some of the results that I recently obtained to as many people as I can. So interrupt, ask questions. You're welcome to do that. So today I will be talking about a new mechanism for electron acceleration that we actually found, and it turned out to be actually the only mechanism known in the literature now to accelerate electrons in the non-relativistic electron-ion shocks. And non-relativistic electron-ion shocks, this happens in many astrophysical objects. When supernova explode, you get non-relativistic electron-ion shocks at some stage in its evolution. When galaxies even merge on a much larger scale, you get these non-relativistic electron-ion shocks. So explaining how electrons are accelerated is basically another way of explaining many of the observations that we see in these situations. So just to motivate why we cared about some plasma instabilities is basically we have these objects. These are charged particles that we call cosmic rays that we observe on Earth, and we have known about for about 100 years now. And the most abundant of these cosmic rays, especially in protons, are these GeV cosmic rays. So if you look at the number density is maximum at the GeV, as you go to higher energy, the number density decreases with some power law. So GeV cosmic rays or cosmic ray protons, basically these are collisionless species, which means that if they stay in the galactic disk, for instance, for about 10 to the 7 years, they basically have maybe few tens to few hundreds collisions, elastic collision with other particles in the thermal gas in the disk. They are more or less collisionless, so there is no binary collision. And these GeV cosmic rays, of course, they travel with the speed of light. So if you estimate the speed of light in some Milky Way type disk, let's say the galactic height is about 3 kbc. See, of course, I wrote this number here. So if people are not familiar, this means that the light crossing time in the disk, so the light crosses the disk in about 1,000 years. So if cosmic rays are traveling with the speed of light, and that's the whole story, they would stay in the galactic disk about 1,000 years. But we know from radioactive dating and also from ratios from spallation product of these cosmic ray primaries that actually they stay in the galactic disk about 2 to 3 10 to the 7 years. So they stay much longer than the light crossing time of the galactic disk. So this means that cosmic rays, even though they are collisionless, they have to strongly couple to the thermal gas in the disk in order to stay that long. And the way they interact, since they don't lose energy, they stay, because we observe them with these high energies, you will need some kind of elastic scattering. So if you have magnetic field irregularities, this is another way of having like this scattering in an energy conserving way. So you have to have some magnetic irregularities that scatter these cosmic rays back and forth, such that the effective transport speed of these cosmic rays is not c, even though individual cosmic rays moving with the speed of light, but much smaller than c. So if you want to explain this, you need to have a mechanism to decrease the effective transport speed from c to like 10 to the minus 4c, something like this. So this, of course, this motivates the study of how magnetic perturbations that can confine these cosmic rays come about. So there is basically two scenarios. One of them is the extrinsic confinement. So basically you get these hydrodynamical waves that you get from turbulence cascade, and this can happen in some merger events. But because it's a cascade, as you go to smaller and smaller scales, the energy in this cascade decreases. And you can show actually that you cannot confine a particle using this scenario with energy below 300 GeV. So if your energy is more than 300 GeVs, you can explain the confinement of these cosmic rays by extrinsic confinement, by turbulent cascade, basically. But the most abundant cosmic rays have energies that's much lower than 300 GeVs. So the other scenario is this intrinsic confinement, and the scenario is basically that these cosmic rays, while they propagate away from their sources, they excite plasma waves through some instabilities. So for example, they can excite alpha waves, and they scatter off of these waves. So they excite them, and then they scatter against them. The scenario, basically, the most common assumption in this scenario is that they isotropize, which means that instead of effectively traveling with the speed of light, they effectively traveling with the local alphinic velocity, because you excite alpha waves. And basically, this is the most important mechanism of confining these GeV cosmic rays, or cosmic rays in the GeV energy range. So in the next part, I will be talking about how you can drive, or what kind of instabilities that you can drive using these cosmic rays. So the rest of the talk, I'll be talking basically inside this intrinsic confinement scenario. So just to start a bit slow, if you have just background plasma of electrons and ions threaded with just magnetic field, you can just uniform system, you can idealize the system a little bit, and then you can ask what kind of waves exist in this system. What does this mean? This means that if I have some perturbation, how does it behave inside the system? And you can see that, and you solve the dispersion relation for this. You can do that mathematically and formally, and you get basically two types of waves. The electrostatic waves, which is basically just a longitudinal perturbation, something that looks like a sound wave, but it's a perturbation in the parallel electric field, in the electric field parallel to the magnetic field. And then you get another branch of waves, which is these electromagnetic waves, something that looks like this, and traveling along the magnetic field, rotating some rotation frequency. And of course, you have two senses of rotation. One of them is R and L. So basically, this is the second branch that you have. So electrostatic waves are interesting, but the problem with them is if cosmic rays scatter against them, they're either gonna lose energy or gain energy. So if you want to have energy conserving scattering, you need to scatter with basically magnetic perturbation, not electrostatic perturbations. Besides, there is also problems with having these electrostatic perturbation growing to very high amplitude. So you don't have enough energy even in them to basically do the job. So if you look at the electromagnetic circular wave that can exist in this system, so in these figures, so basically on the right here, this is the sense of rotation. The R is basically the same sense of rotation that an electron with some perpendicular velocity would rotate around the background magnetic field, and the L is if you have positron or a proton. And if you solve the dispersion relation, which is the solution of the dispersion relation, is basically tells you if you have perturbation of some wavelength, K, the solution of the dispersion relation tells you how fast this perturbation would rotate. So if it is rotating in the same sense as electrons, if you are in the very long wavelengths, these will be Alfvén waves. So the sense of rotation will be such that the phase velocity, which is omega over k, is basically the local Alfvénic velocity. As you go to shorter wavelength, higher k, for the electron sense of rotation, you get these Whistler waves. And these waves that we have also observational evidence for them in the solar wind, for instance. And then after you go to even shorter and shorter wavelengths, once you get this to this electron skin depth scale, which is C over omega E. Omega E is the electron plasma frequency. Basically, the rotation frequency, the rate by which they rotate, saturates at the electron cyclotron frequency for the very short wavelength ones. For the one that rotates as the ions, the story is a bit simpler. If you're in the very long wavelength case, you have Alfvén waves. As you go to shorter and shorter wavelengths, once you hit this is the ion skin depth, which is C over omega I, and omega I is the ion plasma frequency. Once you hit this ion skin depth scale, or you go to scales shorter than it, the rotation frequency saturates at the ion cyclotron frequency. This is basically the kind of waves that can exist in such a system. So now, the question we asked in this paper, basically, okay, if we fire some cosmic rays that have some drift speed, so parallel drift speed, and some perpendicular velocity, which is basically have a parallel along the magnetic field and some perpendicular velocity, which is like, let's say, the parallel to the magnetic field is the x direction, so it has some velocity in the y and the z such that vy squared plus vz squared equal this v perpendicular squared. So this is kind of it's called a gyrotropic cosmic ray distribution. So, and you ask, okay, so if cosmic rays are less abundant, this is the astrophysically interesting case, then the background plasma, so this is why there's lower number of dots here than here, what kind of instabilities can you drive? And why do we expect instabilities there is you have a source of free energy. This drift of cosmic rays, this is a source of free energy, and this source of free energy can excite some waves. This is called the instabilities, and basically uses this source of energy to convert it to a magnetic perturbation amplification. So up to this paper, there was these two known instabilities, this gyro scale instability and the small scale instability. This is at the very long wavelengths, so much smaller, much longer than the ion skin depth, and much smaller than the electron skin depth, which is the small scale instability. These are instabilities were found and refound in the 50s and 60s. Basically, the gyroscale instability is instability that grows on the scale of the gyroscale of ions. And small scale instability is instability that happens at much smaller scales. But what we did, and for these two instabilities, the rotation frequency of the waves that you excite is very slow. So the usual assumption that people did up to this paper, basically our paper here, is to assume that the rotation frequency of these unstable modes is much smaller than this ion gyro frequency. And if you solve the dispersion relation, these are the two stabilities you find, the small scale ones and the gyro scale ones. So what we did was to ask the question, okay, if we don't assume that the rotation frequency of these unstable modes is very small, I just try to solve the dispersion relation, what do I find? And we found a new cosmic ray instability, which we call intermediate scale instability, that happens between basically the ion gyro scale and the electron gyro scale. These two red lines. And it has two peaks, and roughly these two peaks are these two values. So if you solve the dispersion relation, that's complete dispersion relation without assuming anything about the nature of the unstable wave, this is what you find. And these two peaks, you can, just from these values, you can see that these two peaks will, as you increase the drift velocity, this is the degree of the anisotropy. It's basically the ratio of the drift velocity with respect to the local Alfvénic velocity. These two peaks will merge if the square root of the mass ratio over 2 equal the drift speed over VA. So the degree of anisotropy equal maybe 21 something if you have electron-proton plasma. And this is, if you solve the dispersion relation, this is what we find. This is now the V drift over VA is less than this value, and we have this intermediate scale instability with 2 peaks. As you go to larger values of anisotropy.
Mohamad, can I ask you a question? Can
Yes.
you hear me? Yeah.
Yeah.
Mohamad, can you hear me? Yeah.
Yes.
So I was just wondering. What about two-stream instability? Is that one of the ones that you already mentioned, or is that not important here?
No. So two-stream instability will excite parallel electrostatic waves. They will not excite. So this is in the other branch that lots of people argue basically is not very interesting in that, and that's confinement picture, because you need magnetic perturbation, not electrostatic perturbation.
But if it's an instability, it take away energy from cosmic rays, right? So that's the point. That's what you want, right?
It depends. Yeah, it depends on how high how high the amplitude of the electric field magnification in the nonlinear regime. So if you can't go to very high, it is irrelevant, right?
Okay. So you think these are more important?
So typically, when people run these simulations, the very small scale, these Langmuir waves, they saturate at very low level. So basically, you don't have parallel electric field at all.
Okay.
And this is I'm gonna show a simulation where we actually show that this is actually the case indeed. So these instabilities that I'm talking about is in this different branch where you excite electromagnetic waves that are circularly polarized either in the right or the left. So back to the new instability here when that I was trying to characterize. So we have 2 peaks, and these 2 peaks you can just see from these 2 values will merge at this value, and indeed this is what we find. And beyond this value, when you go to higher V drift over VA, this instability saturates. So it's an interesting instability that has a condition on the process. So if the degree of anisotropy is low, so V drift over VA is smaller than the square root of the mass ratio over 2, you have this instability that actually is the most important instability because it has the fastest growth rate, at least in the linear regime, which people have been ignoring when they try to come up with theories based on these linear theories or quasi-linear theories to find a transport, basically effective transport wave of cosmic rays in a stellar or galactic environments. So it's an instability that has some condition, and you can actually classify what is the most important instabilities in different regime. So here alpha is basically the cosmic ray to background density ratio. The MR here is basically the ion to electron mass ratio. Gamma I is the Lorentz factor of ions. And as you can see, if you have small degree of anisotropy, V perpendicular is basically tells you if cosmic ray population have basically a pitch angle or not. So V perpendicular is 0. All cosmic rays are just traveling along the magnetic field. It is non-zero, larger than this value. It has some pitch angle. So you have low degree of anisotropy. If you're just traveling exactly parallel, if you don't have cosmic rays, don't have any pitch angle. The most important one is the gyro scale. But once you have a little bit of pitch angle, this is a very small value because alpha is typically very small. The most important instability is actually the intermediate scale instability. And as you go to very high V drift over VA, very high degree of anisotropy, you get these Bell waves or Bell instabilities and a small scale instabilities. And these are interesting in the vicinity, basically in the vicinity of cosmic ray accelerator. So if you have imagine some cosmic ray accelerator like a supernova explosion or something in the and cosmic rays are traveling with the speed of light, and they have very high, on average, very high V drift over VA, you can excite these Bell modes, but otherwise you don't. So basically, this is different types of instabilities, and what we ask is, okay, so we have linear instability. What does it do to cosmic rays? And there's a kind of found a neat way of trying to look into that. And basically, if you imagine you have an electromagnetic wave that's traveling with phase velocity v phase, and some particle that is traveling with Vx, Vy, and Vz, and you have a magnetic field, background magnetic field along the x direction, you can see that due to the interaction of this particle with the wave, what is the rate of changing the kinetic energy parallel to the magnetic field and perpendicular to the magnetic field, background magnetic field. And you get these two equations. And you can see from this equation that if the phase velocity is the same as the cosmic ray parallel velocity, so if the instabilities excite some modes that are parallelly that are co-moving with the cosmic ray particles, you get this k perpendicular equals 0. So because Vx equal V phase, so this term cancel exactly, and you get only parallel scattering. So if cosmic rays excite electromagnetic waves that are traveling with them, you get this parallel scattering only. But if you excite some wave that, let's say, static in some frame, you get this energy conserving because V parallel the change of the parallel kinetic energy equal minus the change of perpendicular magnetic energy. So this is the energy conserving scattering is usually when you have when you excite Alfvén waves, the waves are traveling with the Alfvén velocity. So in the Alfvén velocity frame, the V phase is 0, and you get this energy conserving scattering. We're gonna see this. We're gonna see if this happens actually in the simulations or not. So what we did was to simulate this just to see what this instability does and whether it actually grows or we did something wrong with the solutions of the dispersion relation. So this is basically a particle and cell simulation that I run with the code I developed when I was in Waterloo. And basically you have this gyrotropic cosmic rays traveling through background electron-ion plasma, treated with some background magnetic field B0. And this is basically the time evolution of the perpendicular magnetic field growth. So as you can see, you have an initial phase that grows very fast, and it's exactly or almost exactly the same rate as you would expect from the linear theory for the intermediate scale instability, and then another growth that is roughly the same as the rate is the same as what you expect for the gyroscale instability. So this is the small scale instability grows fast, and then the large scale instability. And you can see also here, this is at TA, this is during the linear phase of the intermediate scale instability. You get electromagnetic waves on a small scale, a small scale, and this TC is during the linear phase of the gyroscale instability, and you can see that you also magnify larger scale instability. So you have these gyroscale waves, and on top of them, there is this intermediate scale waves. So intermediate scale instability, you can also show using the linear dispersion relation that they are actually ion cyclotron waves that are co-moving with the cosmic rays. So the expectation from that is, since they are co-moving with cosmic rays during the linear phase of the intermediate scale instability, you will have only parallel scattering of cosmic ray ions. And this is indeed what we find. So during the linear phase, so basically the stars here in all these figures is basically the initial momentum distribution of cosmic ray ions in the simulations. And basically this is the cosmic ray ion distribution at different times. So this is during the intermediate scale instability, the linear growth, the saturation, and then the gyroscale instability, linear growth, and then the saturation. The white black lines is basically the energy conserving scattering contours for the background frame, and this is for the Alfvén wave frame, the dashed one. And as you can see that during the growth in the intermediate scale instability, you get this parallel scattering as we expected from theory, and also the average drift speed decreases. You can also quantify that, and it decreases by quite a bit. And during the growth of the gyroscale instability, you can just squint your eye a little bit, or you do some statistics, you can see that actually there is energy conserving scattering along the dotted white lines during the linear phase and the non-linear phase. So basically we simulated both instabilities in the simulation, and we looked at what the nonlinear regime for these two actually tell us about the nature of the saturation of these two instabilities. So just to summarize, what I talked about so far is that we found a new instability that derives co-moving ion cyclotron waves. This happens on the sub-ionoscale depth scale, and it has a condition for the growth, which is basically V drift over VA is less than this number, which is 21 something. And the growth rate of this instability is actually much faster than the gyroscale instability. The gyroscale instability is up to recently, it was thought that this to be the most important instability in this self-confinement picture. And what we found from the instability, from the simulations, is that yes, indeed, we grow these waves as we expect from theory, but also the average lift speed of ions decreases. So what can this do in different astrophysical contexts? So the following maybe 2 slides is going to be some speculation, and this is some speculation that we did in the first paper in 2021. And so this is kind of it's going to be qualitative, so remain to be shown. So since this instability has growth rate that is much larger than the gyroscope instability, this means qualitatively this instability is going to be the most important instability when you try to come up with the propagation models in the interstellar and galactic simulations. And the reason for this is basically because this instability has a growth rate that's much higher. The expected pressure gradient that you would generate due to this instability is much higher, and you can generate a lot of pressure gradients near cosmic ray sources, for instance, and this would of course launch some galactic wind with higher speed, would impact the star formation rates in stellar environments, and also since it increases the scattering frequency because you grow much faster, you grow these waves at a much faster rate, you can also impact the parallel diffusion coefficient, that's K parallel, especially near sources. And there's some observational evidence actually that this is actually the case in many astrophysical objects. So this is just a simulation from Book-et-al. 2019. These are basically Milky Way-like isolated galaxy simulations using this Auriga MHD model plus cosmic rays. And this is just to show how can cosmic rays actually impact. Here is the surface density of gas distribution. So basically, this is all of these panels are the same exact simulation, just different ways of including cosmic rays in these isolated galaxy simulations. And this is the gas distribution in the face on, and this is the edge on one. This first one is basically when you do the simulation without including any cosmic rays. And this is when you include, and basically here we include cosmic rays by exploding stars, injecting some cosmic rays at some 10% of energy from the kinetic energy of these exploding stars with some probability. So here you include in these 3 panels, you include cosmic rays in different ways. So basically the first one here is you add cosmic rays and you allow them to diffuse, and also alpha streams. So when you have alpha waves, you decrease their effective drift speed to local alpha speed. And here when you allow them to only drift, and here when you allow them to only advect, and you can see there is a huge impact on even the visible impact on the gas distribution of the background plasma. And also you can look at the same story. You can see it also in the magnetic field amplifications in these galaxies. So basically, that's also the magnetic field at redshift of 0. Also the distribution face on and edge on, and you can see it has a huge impact on the distribution of where magnetic field is actually amplified, and also how much it amplifies by. So this instability can have a huge impact on basically because of impacting the cosmic ray propagation model, they can have a huge impact on stellar and galactic environments. Another thing that we found from the simulation.
Sorry, can I? Mohamad, yes. Can you go back?
Yes.
Yeah. Could you clarify, I mean, the absence or presence of this instability, how would that, I mean, which one of those pictures would that be relevant for? Or, I mean, it's not quite clear to me, because, I mean, if you have any instability, if it happens fast enough, then you're going to reach equipartition. So, I mean, it might be like 10 times or 20 times faster, but if it happens quickly, then at the end, does it make a difference which instability is it that is doing it?
Yes. So, I mean, yes, that is true. It depends on the nonlinear saturation, but also depend on where the energy after you grow them go. So for this instability, this is one of the results that we found. We found that actually the energy that you grow at this small scale inverse cascade to larger scale. So you grow them very fast on the small scale, and then the inverse cascade on the larger scale. So the energy doesn't thermalize quickly, for instance. So it quickly doesn't have any impact. No, it has inverse cascade, so the energy goes to a larger scale. So in these simulations, this new instability is not included. This was before that we found this instability. But just to say that having different cosmic ray transport model can have a very huge impact on the gas distribution in galaxies, in the simulations of galaxies, and also the magnetic field amplification. So having the correct cosmic ray transport models is really important to get these observables correct, right?
So I mean, that's what I want to understand is having this new instability, would that make diffusion more efficient, or is that just that none of these actually is correct and you have a different implementation that you have to put in? Or what sort of implementation would you be putting in?
So I mean, so this would depend on actually simulating this instability. So what we have now is, so to simulate these instabilities, you have to simulate them in 6D. So 3 velocities, 3 spatial coordinates. So these simulations so far has been in 3 velocity and 1 spatial coordinates. And we found this inverse cascade. And if this story carries to 3D, 3V, this will have a huge impact. So for instance, things will look more like this diffusive alphinic implementation, but the magnetic field we expect to be, the magnification of the magnetic field has to be higher. So if you go to also to the gas distribution, you will have the distribution of gas maybe in the middle a bit higher. But this depends on actually writing down transport, cosmic ray transport theory in the light of the new instability. And this is something we haven't done yet. So this is so far just speculation. And basically these simulations just to show that this speculation can actually have a huge impact, at least in the simulations. And this is important if you want to, you know, compare simulations to observation and to learn something about the physics. Another thing that we found that this instability does is actually quickly decreases the average drift speed of these cosmic rays. And this could also have impact on basically confinement of these cosmic rays. If this happens very quickly, even if it saturates at low level, this means that the cosmic rays near their sources will spend longer time. This would impact some observable like the gramaga of ions around sources, and also the expected emission from these if you have some, I don't know, nearby clouds where cosmic rays scatter and do some emission. Another actually very interesting observation that we made in this paper was that this intermediate scale instability excites these co-moving ion cyclotron waves on a small scale. And the good thing about these these waves is that if you have some neutral in the medium, they don't damp them very quickly. So if you calculate the so-called ion neutral damping is basically how fast you damp some waves due to the friction between the ions, the charged ions that basically support these waves, and the background neutrals, which don't interact with these waves. So due to this friction, you can damp the waves. And we calculate the ion neutral damping for the alpha waves versus the ion neutral damping for these new intermediate scale driven waves. The ion neutral damping of the intermediate scale waves is actually slower by a factor of 1 million. This means that if you have cosmic rays propagating through some partially ionized molecular clouds, for instance, you will not have any alpha waves because of this damping. And we will have actually shown that to explain the abundance of ionized, for example, the lithium, the column density of the lithium in some partially ionized molecular clouds, cosmic rays cannot just be flying with the speed of light there. So there is an observational hint that there is also another instability that doesn't dam due to this ion neutral damping. And basically this instability can actually explain this, but this is a paper actually I'm writing right now, and it looks very promising. Another speculation that I will be talking in the rest of the talk and the rest of the time I have is basically that this instability can actually solve the famous electron injection problem in non-relativistic shocks. So we speculated about this, and in this paper we actually showed that actually it's really important to explain electron acceleration in these shocks. So just to start slow, basically if you have a hydromagnetic shock, basically two plasmas that are traveling at some speed toward each other, you create a shock in the opposite directions, of course, with different speeds in the same directions. And basically in the limit where you have weak background magnetic field, so this is the strong shock limit, so the alphinic Mach number is high, which is basically the shock speed over the alphinic velocity. You get some density compression in the so-called downstream. So one side you will have density 4 times larger than the upstream density, and this means that you have magnification of the local magnetic field in these shocks. So first I want to explain how ions get accelerated in these shocks. So basically in the two sides of the shock, you excite gyroscale modes. So are the first modes I talked about, and basically the first known modes. And these are basically magnetic perturbation that are traveling. So in this side they are traveling toward the shock front, and in that side is traveling toward the shock front, but in the opposite direction. And due to the scattering of these cosmic ray ions with these magnetic clouds from the two sides of the shock, they keep going back and forth. If these magnetic clouds are static, this is the so-called Fermi-1 acceleration, and the rate of energy goes as basically V shock over C squared. And if these magnetic perturbations are actually moving or merging toward the shock front, the rate of the energy, this is called the Fermi, the first one is called Fermi 2, this is the Fermi 1, and here the rate of increasing the energy of the ions is basically V shock over C. So since non-relativistic shocks, let's say V shock over C is 10 to the minus 4, Fermi 1 versus Fermi 2 has like a 10 to the 4 energy rate increase. So this is basically because you excite gyroscale waves on the two sides and scatter ions, this is how you get the acceleration. And the electron injection problem was that since the gyroscale of the ion, if electrons, is much smaller than the gyroscale of the ions by basically the mass ratio, the ions in the upstream or the downstream will not be scattering against these waves, will be just gyrating around them and get transported from the downstream to the upstream or vice versa, without experiencing any reflection across the shocks and thus no acceleration. So what we speculated is because of these instabilities, you excite these small scale waves that actually can scatter these electrons because they are of order of the gyroscale of at these shocks. And we said this can enhance the magnetic field amplifications, the magnetic field amplification at a small scale, and thus electron acceleration. So the good, I mean, there's a simple way to show that this is actually the case was since the instability as a condition is to run some simulations where the instability exists and where the instability doesn't exist, and just compare the magnetic field amplification and electron acceleration in these simulations. So we run 3 simulations where the shock speed was exactly the same, the sonic Mach number was exactly the same. They had either different. So basically, this is the first simulation. This is a simulation where the condition of the instability is satisfied. And since this is an inequality, you can violate this inequality by 2 ways, by either decreasing the mass ratio, and this is what we did in this simulation, or increasing the alphinic Mach number, basically by weakening the background magnetic field. So in all simulations that we run, we had the magnetic field and basically formation of shock precursor on the upstream and shock downstream, which is the density is higher. So on the left here is the number density normalized to the far upstream number density. And here also there is a one component of the perpendicular magnetic field amplification. And this is basically the XT diagram. So basically this gives you the evolution of the shock too. And in all of them, you form shock front, shock downstream, you get magnetic field amplification. But of course, you don't see the small scale modes and what they do from this figure. I'm gonna skip this. This is basically the solution of the dispersion relation, how I decided to run these simulations, but this is basically the simulation result. So the red simulation, this is the simulation that satisfies the condition for the intermediate scale instability. The blue simulation is where the condition is satisfied by increasing the alpinic Mach number. The black simulation is where the condition was dissatisfied by decreasing the mass ratio. And in the bottom here is basically the Fourier component in the downstream region. So basically how much power I have in the magnetic field perturbation at different wavelengths at some particular time during the evolution. And as you can see, when you satisfy the condition for the intermediate scale instability, you have a lot of power at the small scale in the perpendicular magnetic field amplification. And this is directly reflected in here. You have a much larger fraction of electrons are actually accelerated at these shocks compared to the blue simulation and the black simulation where you don't have this intermediate scale instability. So only the simulation that satisfies the condition for the instability have this very efficient electron acceleration and a lot of magnetic power at smaller scale. Sure, this is what we expect. So this is a movie that I'm gonna run for this red simulation where electrons are efficiently accelerated. And basically here I show the momentum distribution in different regions. So I call this, this is the shock front region, this is the downstream, this is the up to some light crossing time of the incident particle, the shock precursor, and I plot just the momentum distribution of electrons in red and ions in black. So basically at the beginning here, you can see magnetic field amplification and some density compression, and you start accelerating ions and electrons, heating and acceleration, of course. And on top, basically. I want to go back a little bit just to make another point. So as you can see from this movie, that ion acceleration is happening at the shock front here, because the gyroscale waves are excited here and there, and basically ions get scattered here. But since these small scale waves are actually traveling toward the shock downstream, you get electron acceleration everywhere. So basically, if you look at the ion density, momentum distribution in the shock downstream here, you don't have that many accelerated ions, but you have a lot of accelerated electrons here. So it's a mechanism for efficient electron acceleration that happens not just at the shock front, it's also in the downstream region. So this is what we show. So what we showed. So to quantify how much energy gain that we got in different simulations. So basically, this is in the red simulation still. This is in the dashed and the solid red lines curves. This is the rest frame momentum distribution of ions and electrons in the simulation, and the black is basically the Maxwell-Joutner distribution. So in this U to the 4FU, the peak of the distribution gives you the temperature of the Maxwell-Joutner distribution, and you can plot using the temperature of the Maxwell-Joutner distribution, and this is basically the black curve for two different temperatures. So to quantify the non-thermal energy fraction, I just go 5 times larger and just take the energy in here and here. So basically, and I can take the ratio between them and can say what is the ratio between non-thermal energy and the electrons with respect to the non-thermal energy in the ions. So this figure shows this time evolution of this quantity in the downstream. And the thing I want you to notice is that all these shocks have exactly the same sonic Mach number, exactly the same shock speed. they have very different acceleration efficiency for electrons. Only the simulations where
Can you take a pause for a moment?
sorry?
Oh, yeah, it got back somehow.
Yeah. Okay, let me try this. Give me 10 seconds to try this.
Okay.
This yes, so the microphone just swapped. Can you try speaking
Okay.
again?
Okay, can you hear me now?
Yeah, so maybe like rewind a minute and say it again. Sorry about that.
Okay. Where did I get cut off?
You got through the left half of that slide.
Okay, I see. So basically on the right side, I plot basically the evolution of this quantity in the three different simulations. So these simulations, all of these simulations have exactly the same sonic Mach number, have exactly the same shock speed. They differ only in whether they satisfy the alphinic Mach number is such that they satisfy the condition for the instability or not. And you can see that only the red simulation that satisfy this instability have maybe 100 times or even larger KEI, basically energy of in the non-thermal electrons versus non-thermal ions. So this is in this figure I showed basically the temperature evolution for basically ions in dashed and electrons as a solid in the three different simulations. This is the red, black, blue simulations. And these dotted lines is basically if all the kinetic energy in the shock gets converted to heat in the downstream, the dashed line is basically what is the temperature that you would expect. So this is what I call MHD. This, of course, depends on the mass ratio because this changes the kinetic energy in the incident plasma. You get these two. And you can see in all simulations, you saturate at a smaller fraction. And the reason for this missing kind of energy is basically because some of this initial kinetic energy is actually goes to acceleration, which when you calculate this saturation temperature, you don't account for. So this is the simulation. And what I want you to notice is that the electron and the ion temperature in the shocks that satisfy with the realistic mass that satisfies or not satisfy the instability condition is almost identical, but they have very different acceleration efficiency. And basically what we got for the TE over TI for the simulations with realistic mass ratios is this, and this is consistent with some observational evidence. And what we, as a kind of a byproduct of this simulation, is we showed that usually people use very low ion to electron mass ratio. And in this black simulation shows that actually if you do that, you get acceleration wrong. And you get also the heating of the electrons and ions wrong. So TE over TI, which is one of the observational observables in some shocks, is wrong also in the simulations. So just I will conclude now. So basically I showed you that we found a new instability that excites electromagnetic, co-moving electromagnetic ion cyclotron waves on the scales that's smaller than the ion skin depth. This basically provided a mechanism. It's actually the only known mechanism so far to have efficient electron acceleration at parallel shocks. And if you use, as commonly done in simulations, low mass ratio, actually get the heating and acceleration physics wrong. And more potential impacts are coming. So stay tuned for my reports about this instability. Thank you.
All right, that was a wonderful talk, Mohamad. Are there any questions from the audience? Make sure that the chat's online. Any questions? Avery.
So this is fantastic, and you alluded to, I think, at the midway point, the need for full 3D, 3V simulations to answer some of the the questions for cosmic wave propagation. Are
Yeah.
those also necessary or useful to say something about shock, electron acceleration of shocks? And what do you, where are you in producing those? And what is your intuition about how they'll differ?
So, so if you think about just the linear phase of the instabilities, they are irrelevant. And the reason for this is you can actually theoretically show that in the linear phase, any modes that propagate just a little bit off the magnetic field direction are quickly damned. So in the linear phase, you grow only modes that we can simulate. But where it is important, I think, is the nonlinear saturation. Because what we found is that this instability saturates by inverse cascading the power to longer scale. And if the cascade story is different in higher dimension, which we think it will, then the nonlinear saturation of this instability is going to be important. So if you think about the full nonlinear problem, it is going to be important. And the simulation now at the stage where we can run 2D 3V, not 3D 3V. And we think it can also capture important physics here. But it's still at this point, it's still speculation. But we think it's going to be important. So this is why I'm working on that too.
Thank you.
So can I ask something about this deceleration, or sorry, acceleration problem you mentioned? So what is it actually? I don't know anything about it. I hadn't heard about it before.
The electron injection problem, electron acceleration problem.
So what is the problem?
The problem is that if you have only gyroscale waves on the two sides, these are the gyroscale of the ions, electrons are not going to be scattered back and forth across the shock. And the reason for that is their gyroscale is going to be small. So if you have a long scale wave and electrons have a small gyroscale, they're actually not going to scatter. They're just going to rotate around them and just ride the wave and go from the downstream to the upstream, and then they fly on. So if you don't have scattering across the shock, you don't get acceleration. But of course, observationally, we know that electrons are accelerated at these shocks. And now from theory, we know that they are.
Okay, so now you have an explanation for that then.
Yes, exactly. Yeah.
And is the only observable is this temperature ratio that you mentioned, temperature of electrons to ions, that you can reproduce that? Is that the idea, or the other observables?
I mean, so to explain, for instance, some radio observation in galaxies, you have to basically assume some value of this key EI that I computed in the simulation, this quantity. And so to explain some radio observations in galaxies. So the temperature, if you observe just the shock, and we have some observational, and this is consistent with them, these are Palmer line dominated shocks that we have observational for, but also basically the non-thermal energy and the non-thermal energy fraction for the ions, because in modeling for let's say radio observation in galaxies or even in ISM simulations, you have to assume some value for this. And what we're saying here is this value is not just a constant value, it depends on the local alphabetic Mach number, and you have to take account for this to basically include the correct physics there.
I see. Thank you.
Yeah.
Very, very interesting.
Thanks. Thanks for the question.
More questions?
So I have just a visualization question. So now I understand in some sort of hand-wavy way what the two-stream instability is. Right? We have a mode, a backwards propagating mode that's being dragged forward by the beam, and that becomes resonant with a forward-moving background plasma mode. Is there a similar kind of qualitative picture for this intermediate scale instability? I was trying to figure it out from your velocities, but I didn't quite get there in time.
I mean, it's a kind of resonance, right? So basically, it is driven by cosmic ray ions that they are rotating like this, and it is so the rotation frequency is the rotation frequency for the ions, and it is co-moving. So the waves are co-moving with the ions. So if you imagine some cosmic ray ions that is traveling parallel to the magnetic field, and it's rotating with some rate, these waves are basically generated with rotation rate that is exactly the same, and they're traveling with the ions. So it's basically it's a resonance between the background ions and the cosmic ray ions propagating, and you can show this from the dispersion relation. It is when you solve the dispersion relation, these are the two terms that are dominant in the solution, or they have the highest values in the solution. So these are the two terms that balance, basically. So it's basically balance between this perturbation and the particle. It's just an electromagnetic resonance, basically. What you're talking about is electrostatic resonance. This is electromagnetic resonance. It's kind of a version of it.
Okay, thanks.
But of course, this doesn't explain the scale. This is something that I haven't figured out. Why is it at these scales and not different scales, basically?
So Mohamad, are you going to visit us back soon?
Maybe in the winter, yes.
Winter, okay.
Yeah.
You miss snow?
Very much. I'm in Egypt now, so I miss it very much. It's still really hot here.
All right, well, I think that's it. Let's thank Mohamad again.